Hi everyone. My name is Adi Singh. Welcome to Ubuntu Masters for the month of June. This is our second session for the day, and I will be the moderator. I'm the product manager for robotics and automotive at Canonical, and I'm very excited to have with me today Zachary Keeton, who is the Yonder Group lead for Plus One Robotics. Thank you for joining us, Zach, and he will
Hello.
be talking to us about how to trim time to market by how Plus One Robotics trim time to market by using open source components in their code. A few housekeeping matters before I give Zach the floor. Um, so this talk, like all our other Ubuntu Masters session, will be an hour long. The first half of the session will be the talk itself, first 30 minutes, 40 minutes, and then we'll use the remainder of the time for questions. So I encourage you to ask your questions using the questions tab, questions option below the screen, and I'll get to them. I'll get to them at the end of the talk. I'll keep looking at them during the talk so as to prioritize them, and then we'll see how many we get and how many we are able to go through during the question answer session. Um, I'd like to remind you that this session is being recorded, and you will receive the recording automatically after the end of the session. Also, feel free to check out the resources in the attachments tab beneath the screen. And in case you're feeling lively and want to join a group discussion, join our Ubuntu Masters channel on Telegram. I believe that information has already been provided in the information tab. And that's that. So without further ado, I will let Zach present.
Hello, everyone. Greetings from my home office here in Texas. We've been stuck in here for a few months now during this COVID period. Hope you all are well. My name is Zachary Keeton. I'm a self-taught web dev. Been doing it for about 12 years professionally now. Several different teams, many projects across multiple different industries. I really love Linux and JavaScript. I use Ubuntu for my personal and business machines. And I'm currently in charge of this cloud initiative for Plus One Robotics, which is a startup here in San Antonio. And it's really the main character of our story today about how the three founders had an idea and we took it to MVP and how we iterated upon that MVP and got to a production grade offering in a short time and on a budget. And it was largely thanks to the open source community, which is great. So let's get started. First, a bit of context. There are many areas of robotics application. One of them is in induction, right? Induction is the idea of taking the raw materials, like these tickets here, and feeding them into the machinery. The same holds true for factory type setting, where you have trucks delivering raw materials, and they have to be manually fed into the machinery, i.e. the conveyances of the factory, right? And here we see a person manually taking the items out of the bin and placing them onto the rollers here. And notice there are random items in random shapes and sizes of various orientations. Yes, it's exaggerated a bit for the slideshow here, but you call this random bin picking, which is you're picking these random items and random sizes and placing them onto somewhere else, right? In this case, the rollers. The downside to this is that this job and task is very repetitive, very monotonous, and it does take a toll on the body after a while. So there's high turnover right here. But this task that is repetitive is a great candidate for potential automation. So if we start with a robot arm, it's going to expect some inputs and it's going to manipulate these items in some way and send them off as outputs. Notice here they start with, for example, one orientation. They're pretty close together, and then on the outputs they're flipped around and spread apart, right? These robot arms, like you see here, so-called industrial robots that do work in factory settings or work settings. We call this traditional robotics, and you'll do code on these with C, C++, Python, and some libraries that are involved motion planning or pose or orientation type programming, like Move It, right, is an open source package that's popular for that kind of thing. And you'll see these are the traditional robots that you've seen in the past, right? Like for building cars or on an assembly line. And the point here is that the inputs you see are very uniform and consistent. These robots are essentially deaf and blind, right? And they might have some lasers or some IO triggers that will tell them when things have arrived or when things have left. But the important piece and the required piece to this kind of setup is the environment has to be very static and consistent and controlled. Notice in the picture on the bottom left, the car bodies are coming in at regular intervals. They're regular distances apart and carefully timed. And the same goes with the picture on the bottom right. You have to take great pains to set up the environment so that it is very consistent and very expected, right, for these robots to do their job effectively. Now, what happens in a setting like we saw earlier, where you have jumbled items, various sizes, various orientations, right, piled on top of each other? How are we going to do that random bin picking with a robot, right, and create this consistent output? And this random bin picking with a robot, like we saw the human doing earlier, is called by some to be the whole holy grail of robot picking, right? We got to get random bin picking. The problem is that we lose all that consistency that we had before. They're all jumbled. It's all random. So with traditional robot programming, we're going to be, confused. Hence the question marks up there. It's going to try to pick in regular intervals. How does it decide? So these robots need to be able to see, essentially. So what we do is we put cameras, right? And they're actually 3D cameras, like you see on some popular gaming systems, on the input and the outputs, connected to essentially an Ubuntu machine, right? Connect that into the robot. And from there, you can code some intelligence, right? Even some machine learning against it. So you get these via the 3D cameras, right? So-called point clouds, right? Where they emit some light rays, infrared light rays, to then bounce back, right? Kind of like echolocation, but with light. And it shows you the depth. And you get this point cloud, and it's a 3D camera, right? And then you can do some calculations on there and some geometry, plane segmentation, etc., to try to distinguish shapes, right, in that point cloud. And also the cameras will give you some RGB images, right? So just the regular color image of the scene. And on there, you can do all types of modern machine learning things like, right, image classification, object detection, object classification, etc., like you see up there with these so-called bounding boxes around the various vehicles, right? And they're labeled, and even the road sign. And the open source libraries here and things we depend on are, of course, Ubuntu for the base operating system. PCL is a point cloud library, right? It's an open source thing to manage and work with those point clouds, right? To write code on top of those, make it more intelligent, do some 3D geometry on it. TensorFlow and OpenCV are machine learning libraries. TensorFlow is a general one, and OpenCV is for CV for computer vision, right? And perhaps the most important open source package for robotics is ROS, the Robot Operating System. It provides a communication layer that gives you modularity between hardware and software components, so you can swap things out, be the brand of cameras, the whole robot arm, or certain software subsystems, without affecting the other pieces. So they click in like puzzle pieces. Gives you a great decoupling and modularity. There's some other Ubuntu Masters talks that dive into ROS into more detail. So you put it all together and you get random bin picking, right? With the point clouds, with the geometry, with the cameras and everything, which is great. And we can get up to 90 to 95% success rate this way. But what about the other times? If it sees something it's not used to or something else goes wrong, it will essentially get confused and simply stop in its tracks or get stuck in a loop. So while achieving 90-95% success rate for random bin picking with a robot is something to celebrate as a data scientist, actually putting these robots into client facilities was actually kind of a no-go, because these clients, with considering that they might have up to 10% downtime, started thinking about the actual dollars that represented, and it was essentially a blocker for them. So that was a big problem for any would-be robotic startups. And this is exactly where the three founders, Eric, Sean, and Paul, had their great idea. Their idea was those few times where the onboard vision system failed and didn't know what to do next, instead of just having the robot stop and do nothing, it would just pause for 5 seconds while it sends a request through the cloud to a human. The human would have a web app in the browser, and the human would receive an image of what the robot sees, right? It says, "Human, this is what I know. Please tell me what to do next." The human could then respond, and the robot could get back to work. On top of that, the responses from the human along with those images would be saved and could eventually be turned into training data, right, back into those machine learning models, make the robots smarter eventually, and then have to call for help fewer and fewer times, allowing one human to then be able to manage, or we call it crew chief, multiple robots, right? So whenever this crew of robots would need help here and there, the one human crew chief could respond, give them help, and then of course save that for future learning. So how do we go about building the MVP for this solution? So remember, in the current robot setup, we're using ROS, the robot operating system, for a message bus layer. So the first thing we do is build in a so-called web bridge, which will click into a ROS service. So then if another system or the robot wants to request this human help, they would send that request to a ROS service that would then be handled by this web bridge. This web bridge then takes that ROS requests and transforms it into a web request that's sent to the cloud. And this first cloud architecture was a serverless architecture. It hits a GraphQL API, and each API endpoint is handled by one of several resolver functions. And again, these are serverless functions written in Python. What that means is, essentially, is serverless doesn't mean there are no servers, right? It just means that you don't have to worry about the servers at all. You just set up these serverless functions that just run in the cloud for you whenever they're called. And all the server considerations or virtual machines that undergird this infrastructure here, they're totally abstracted away from you as the quote cloud native developer, right? So things like load balancing or auto scaling are handled for you. It's one of the pros of the serverless type system. So these resolver functions run whenever they're called, and then they then depend on certain other serverless services, right? Like there's a database service or a storage service or an email service, and then your code in these resolver functions just have APIs that it uses to then access these other services in the backend. And again, This, you don't have to set these up. You don't have to set up these database services. As far as the actual infrastructure item, like the database server, for instance. You just call the database service and it handles it for you. And if somehow your site or product becomes super popular overnight, say it gets some kind of press release or goes viral somehow, and you get bombarded with traffic, these serverless infrastructures can just handle that for you, right? They'll auto scale. Then on the other end, the user, right, the human crew chief, we call it, would be on the laptop and hit a URL in the browser, and that would hit another web app, right, service up there in the cloud. And so that would fetch back into their browser and render, and then be a web app, and then that web app would then call the API. And in this MVP version, the web app would do some polling, right, to actually this queue service here. Whenever the robot would request help, right, that request would be added to this queue, and in this MVP again, the browser would poll the queue at regular intervals to get the request that then the human would see and respond to. And then these would make their way back to the robot, and the robot would continue working. So the pros of this first MVP kind of setup was that they are relatively easy to do. So again, at the beginning, when you have a robotics startup, they don't have a gigantic team of web developers, right? Roboticists, they're used to C, C++, and Python, right? That's why it's part of the reason why most of this was written in Python in the cloud, right? They had a roboticist type people that knew a bit about the cloud, so they wrote it that way, and that's what they had. And they could set this up in the cloud. You go to these web consoles and configure your services and whatnot, and hook them together and just push your code to these different places, and it just works for you. So again, you get a lot of things for free. There are a lot of easy buttons with the serverless type architecture. So one of the big easy buttons was like the authentication service, right? You could wrap up your web app with authentication and have users register, change their passwords, and all that kind of authentication stuff, along with other things like emails and the logging, right? So if you had to debug, there's rich logs available to you to go mine and try to find issues and whatnot. So you got plenty of things, quote, for free. And what that gave them was speed to MVP, speed to market, right? To get out to these first customers, to try and really get that feedback and understand whether or not they had, a first inclination of a product market fit. And the serverless offerings are relatively low cost. Most of the time you're paying for by request. And at the beginning, when you're doing MVP type stuff, you're not doing as many as request. You're not handling millions of requests per second yet, right? So relatively low cost to get an MVP out the door. And most importantly, it just worked, right? So the robots were able to call for help from a human. The human was able to respond and was able to get back. And they were able to get this to their first kind of beachhead customers to try it out, early adopters, and get that vital feedback, like you learn with all the lean startup best practices and whatnot. So it did serve its purpose. There are some cons that they encountered with the MVP and serverless architecture in general. For one, this piecemeal solution that they built as they went along, you really can't run all of this on your dev laptop. It's meant to be run in the cloud. You're meant to dev a little bit, push it up, see it run. This cloud native development. The problem is that the dev cycle times were a bit long, And also, in my mind, the main con was you had strong vendor lock-in, right? So these APIs for these services are specific to this cloud vendor, right? And so eventually, and we'll get this in the next slide, but certain customers might not want their data in that specific cloud vendor's offering, right? So they might want to pick a different one. So you don't have much portability in this case. So it depends on your use case, of course. So in certain instances, I would highly recommend a serverless architecture like this, especially the idea of abstracting away all that kind of IT infrastructure and scaling and whatnot. You kind of offload that to the vendor, and that's pretty nice. But once we got this out to the customers, then you wanted to make another develop cloud, right, for more features to be added, and then to kind of turn this into the de facto production cloud, for the time being. And again, when we built that in piece by piece, they had a hard time redoing it, duplicating it out. So it became painful to do, error prone, and time consuming, because every time you wanted to change something, you'd have to upload the thing, and if something went wrong, there would be auto rollbacks, and you'd have to wait for all those processes to complete. Also, each of these serverless functions in the startups source control, right? Managers, they had their own repos, right? We use GitLab. So and GitLab's another great open source thing. So GitLab had individual repositories for each one of these serverless functions and more. So we had lots of different repos to keep in sync, and there was minimal CI/CD, minimal unit testing, and again, it is MVP, right? You want to fail fast, you want to get it to market fast. So this did serve its purpose. But then moving forward, after you understand that there is that product market fit and there is kind of a viable path forward as far as you want to keep going down this route, you start getting other considerations, right? So now we have to hire more web devs, and over here in the front end, we have React and GraphQL, and which are open source things from Facebook, which is great. Right, another way that open source offerings helped speed us along down our path to market. But now you have to hire web devs and then Python devs, and it gets kind of rough when you have to deal with multiple languages. Of course, Python's not that hard to learn, but it's just some added friction, so it just counts in the cons list. After we verified the product market fit, it was time to iterate on the MVP. So we started by rewriting everything in JavaScript, from the web app, the server, and even the web bridge are now in JavaScript. This helped us with code reuse, and it made hiring developers easier, because even if you had a developer that was initially only strong in the front end, they could eventually work in the back end since it was all JavaScript. This helped us get a whole lot done with a relatively small web dev team. So starting again on the robot side, remember that we have an Ubuntu host OS, right, running ROS as a communication layer between these various robot services, and our web bridge is just offering a ROS service with a defined request and response data structures. So we rewrote this web bridge in Node.js using the ROS Node.js open source package that allows you to make a ROS node out of JavaScript instead of Python. And we knew, though, that we were going to be using the GraphQL subscriptions, right, which use observables, which essentially act like event streams. And we could handle the requests coming in from the ROS side as event streams also. So we went ahead and made a wrapper around the ROS Node.js package, which is promise-based. We wrapped it with RxJS to leverage that observer pattern on both sides. And the best part of all this was thanks to Ross, and that defined request and response data structures in the service. This new web bridge could essentially just click into place and replace the older Python one, and the other robot systems wouldn't know the difference. They still just made a ROS request, service request and response the same way as they did before. And since those data structures were the same, nobody else knew the difference, that it was a whole new web bridge. So now onto the cloud. Remember we said that each resolver function had its own repo and that it was complicated to manage all these pieces separately. So we went ahead and gathered the resolvers and the web app and even the web bridge into one mono repo. And this allowed increased code reuse and also eliminated that overhead incurred by having to manage all these code repositories independently. Again, we're trying to maximize efficiency with a relatively small team. Since we can easily reuse code now across the resolvers, we wrapped the vendor-specific services into a new service layer which could be mocked during unit testing, which we also improved. So for unit testing in the front end, we used Jest, which comes with the React.js, to do unit tests in the browser. But what's really nice is that Jest has a quote node mode that allows you to use Jest as a unit test runner, not only in the browser, but also on the servers too for your Node.js functions. So we were able to use Jest also in the API server, these resolver functions, and also even in the web bridge. So that was great in that it allowed skill transfer for the web devs to go all the way down the stack. So they could learn one unit test technology and apply it all the way down. We also use Redux Saga and Apollo client to do some asynchronous data fetching to the API right from the front end. But we soon noticed that most of this API client code that we use in the front end, we can reuse it also between the web bridge and the API. So we went ahead and created a single API client package that can be used for both. That's another reason to love JavaScript. The same package can run both in the browser, right, and in the web bridge and use the same code. If we were to decide later to make other clients, say native mobile apps, having this client library available will of course be a huge time saver. We also got rid of the polling in favor of the GraphQL subscriptions, which use Reb sockets to create the observable event streams I mentioned earlier. This allows the real-time crew chief notification when a robot makes a new request, and it also enables real-time responses returning back to the robot. Finally, we were able to script the entire cloud deployment process so we could essentially press one button and hydrate a whole new cloud deployment for us. This made it easy for each developer to have their own cloud for different features or different test deployments, etc. So we have a whole list of improvements that we made, but we still have a few persistent cons, right? One is we can still pretty much only run all this code in the cloud. Like I said, even though we scripted the cloud deployment and each developer can have their own cloud, you really have to still wait for your code to deploy to the cloud, run it. If there's any build time errors, there's going to be a rollback, right? Or you get it up in the cloud deployed, you run it yourself and test it manually, kind of developer alpha testing. Something goes wrong, you have to edit it back on your local machine, then redeploy again. It's very time consuming. And then also, we still haven't solved at all this vendor lock-in. So even though we've wrapped our services, right, there are still vendor specific service APIs under the hood, and our code is still not as portable as it could be. And during this time in the timeline of the startup, the main requests coming from these would-be clients are things like, well, I want to pick my own cloud, or can we do it completely on-prem, right, and not have our data in the cloud at all? So we had to come up with a different solution to not have to turn away business, which as a startup, it's definitely something you want to avoid. The way we solved our vendor lock-in problem was essentially with Docker and Kubernetes. So we had to Dockerize each service and replace all those easy button vendor-specific services with various open source alternatives. In the web app, we use Nginx as a reverse proxy. In the API server, we used Apollo server for the GraphQL, Passport.js for the authentication, NodeMailer for the email service, Winston for the logger service. And then for the persistence layer, we have Mongoose and MongoDB. And handling the certificates is another open source package called Cert Manager. Once we had everything Dockerized, Kubernetes knits them all together. It handles the communications between the containers and between the overall deployment in the outside world via an Nginx ingress. It handles fault tolerance, load balancing, and even the clustering across multiple virtual machines on the cloud that you'd have to manage now. Yep, and that's one of the new cons. So unlike with serverless architecture, where all that IT concern was abstracted away from you, you will have to be dealing with some virtual machines with your cloud vendor. And even though there's auto scaling and it's not that hard, but there's also relatively higher cloud costs, right? Because now you're essentially renting these VMs by the minute versus paying per request, like with the serverless setup. But you do escape the vendor lock-in, right? All the major cloud providers can run Kubernetes. You can even do it on bare metal, which enable on-prem deployment, and even on dev machines, we'll see in a minute, with much shorter dev cycles. The developers have a much easier time working with Kubernetes because they can run it all on their own box. Here's a developer with an Ubuntu laptop, which is what we use every day. We start with adding in Minikube, which is a virtual machine that essentially acts as a single node cluster for Kubernetes. Then you add on top of that a command line program, kubectl or kubectl, that acts as the API to control Kubernetes inside Minikube. And what it does is it ingests so-called manifest files that describe the Kubernetes deployment. So that's how it would know to build all your pieces. This is so-called infrastructure as code. Then we would add on Helm, and we use Helm to dynamically generate those manifest files. So Helm lets you inject variable values or set flags, things like that, to make these files dynamic. Then on top of Helm, you can add in Scaffold. Scaffold does a lot of things, but we use it for mainly a dev tool to enable hot reloading. So if we have our IDE, Visual Studio Code is what we use. Again, open source from Microsoft. So if you or a developer were to change the code in the IDE and press save, Scaffold's watching that code and then would be able to, via Helm and kubectl or kubectl, update the cluster, update the deployment, and even hot reload your browser, right? So before, with the serverless setup, a developer would have to change some code and upload to the cloud with possible robots, etc. So that dev cycle could take up to 15 minutes to see an update in the cloud, whereas here it's just a few seconds, right? And so it's much faster for the developers. Also, they can just simply add in another Docker container for the web bridge with a dummy robot script that we have that can send requests to that ROS service that this bridge handles. So we can mimic robot requests to the web bridge, which would go into this kind of local cloud that's on this developer's laptop here, and see that in the browser and then respond, all while we are updating code and hot reloading. So this development workflow is much more efficient, and all developers essentially have their own clouds on their own machine. And as an added bonus, the kubectl and Helm command line tools work against a so-called context, i.e. you just aim it at a target. Right now we're aimed at the Minikube context. Well, the commands that you fire against Minikube are the same commands you would fire against any context, i.e. a cloud context, right? So as a developer is working with these Kubernetes tools and doing things like deploying and updating and rolling back and managing their own kind of local cloud cluster here, they are going through the motions and learning the same commands that they would use against a production cloud, right? That is off-prem. So each developer is essentially gaining operational skills and could potentially stand in for an operations or a DevOps engineer if needed. Which again, as a startup, having that extra capacity for your team is very cost effective. When the developers do finally push their code up to the SCM, we use GitLab. The fact that everything is containerized allows for a very rich CI/CD pipeline. Each tier of the application runs through its own unit tests, for which we have coverage thresholds. That means if devs were to push code with insufficient test coverage, the pipeline will fail right here until they add enough unit tests to satisfy the coverage threshold. Then Docker images are created and the NPM packages are created and pushed to the private registries that GitLab offers. Then we could choose to auto-deploy to a cloud staging area against which we can run integration and end-to-end tests. We're using Postman and Newman for the API integration tests and Puppeteer for the end-to-end web app tests. And if QA or test engineers wanted to test locally, they could simply pull those images from that Docker registry onto their local machine and stand up their own Minikube cloud instance like the developers do, and either test on their box or test straight against the staging stack. Either way, it's nice because the developer environment and the QA environment closely mirror the production environment, so there's no surprises there because everything's going to run the same, and we have no works on my machine problems, right, because of the containerization, which is nice. Then the web bridge, seeing that it works against ROS and those defined service requests and response structures, when we are ready to test against the live robot, we can rest assured that the web bridge will just click into place, right, amongst those other robot systems and play nicely. So this entails a very efficient, very high velocity development workflow. And there you have it. That's how we went from MVP to a cloud vendor agnostic real-time cloud solution to get robots in the field faster, keep them working when they get confused, and to eventually help make them smarter, all while trying to maximize developer skill transfer and team capacity, especially when working with a small team, while minimizing wasted time and cost. And all this is due in large part to the generous contributions of the open source community. We touched on many of these packages, some of them we did not, but their generosity is helping move progress forward much faster than it would have without them. And a big thanks to, of course, Ubuntu from Canonical, on which all this happens. The robot code runs and the development gets done. Thank you very much.
All right, Zachary, thank you so much for that wonderfully interesting talk. I really appreciate uh, the abundant use of open source components in your stack. You talked about Ubuntu, ROS, OpenCV, PCL, TensorFlow, Node.js, Kubernetes, and weaving Canonical. We love that. We love hearing the people using open source and not just using open source, but actually building stuff that gets companies and enterprises to production, right? And so you weren't just hacking away in your lab. You actually were able to create something very useful, very practical for your customers. So, kudos to you for that, and we love hearing that. But what's interesting is the stack that you mentioned, the various stacks that you mentioned throughout the process. They aren't something that is unique or to Plus One Robotics. It's not something that you guys just dug out of the ground. They're actually very common tools in the developer community and are used very widely. So I think a lot of the value propositions that you spoke about and the obstacles that you spoke about and also their solutions are very relevant to our audience and to the community. So on that note, I see there's a stream of questions coming from the audience. Thank you, audience, for that. We'll try to get through as many of them as possible in the next 18 minutes. So let's start with that. So we are asked, Zach, I think this came in during the MVP slide. Are the instructions used by the bots stored locally on the machine or contained in the cloud?
Right, that's a good question. So again, we have the robots working as autonomously as they can, right? So they have onboard computer vision systems. So they are trying to work it out for themselves as much as possible, right? So it's only when they need that help, right, from the human that they call up to the cloud and get that human help comes back. So any kind of help requests and responses are then saved in the cloud to then be recaptured for future learning, but all the rest is on the edge system. Yep.
Right. Yeah, and it's quite interesting how you actually use these responses from the human also as part of your training set to continuously enhance the ability of your robot. So over time, I imagine the number of requests that the robots make to the human user operator, they continuously decrease, and that would be the aim, right?
Right. So that's the idea, right? So you want them to improve over time.
Mhm.
And I'll be honest, right now there's this notion of active learning, wherein the human it's probably what you're imagining it does now, which is where the human responds, it gets back to the robot, and it's immediately reincorporated into that machine learning model, right? And then those gains are realized immediately.
Mhm.
The truth is we're not there yet because there's a potential right now for the robot to sort of learn in the wrong direction, right?
Mhm.
So what we need to do now, and the goal would be the active learning eventually. But for now, what we do is we extract the learning, and we would have to do an in-lab, right, model training and testing to make sure that it would be a net improvement, right, before we push it out to client robots.
I see. So you actually validate the learnings before you actually deploy them to the robot. It's not that you just trust the robot to do the learning itself while it's out in the field.
Right, because you're dealing with live client facilities who are worried about continuous throughput, and that's their daily operations, right? They don't want any surprises, right?
Yeah, and when you were talking about the 90% success rate, which makes data scientists happy but not clients. I come from an automotive background, and even 99% wouldn't make people happy. You'll have a lot of people annoyed unless it's 5 nines or something like that.
Exactly.
We have another question, fairly small one. Is reinforcement learning being used to control the robot arm? Or I bet to teach the robot arm?
So I'll say not yet, but we do have some very brilliant roboticists on our team that have sketched up these reinforcement learning kind of scenarios or strategies. Again, I'm the web cloud guy, the lead, right? So I'd be happy to field some questions. I'd be happy to, kind of pivot your questions to the roboticists on our team if you like. The email was on the slide, zachary.keeton@plus1robotics.com. I'm sure they'll be happy to talk with you about that all day long.
Wonderful. Yeah, I'm sure they would. So we have a bunch of other ROS-specific questions coming up, but let me just change tracks a little and come back to the open source aspect of it. Um, you know, we are very, we consider ourselves domain experts in open source software, but we do recognize that there are pitfalls that companies can have when you're adopting open source software into building something that's production based. So what are some of the pitfalls in your experience that someone can experience while using open source software? And then, but don't just leave the answer there. Also tell us how you solve it. So what can our audience do to actually solve those pitfalls?
Right. So open source is great because instead of reinventing all these wheels, very smart people have created these packages, and they're very well tested and vetted, and you can just use them, and then your own business logic will go on top of that and glue them together, right, to make your own product. And my favorite part about that is all these things that I mentioned, somebody can use them at home, right, in their garage to make their new prototypes for their new things. So overall, I think the net value of the open source far outweighs the problems, but there are some, right, which is security mainly. So when you're using the open source ecosystem, especially in JavaScript, so some people will make fun of JavaScript that there's a lot of dependencies and dependencies of dependencies and so on, right? There's plenty of memes and jokes about it. But the worry is that when you're relying on these packages that are maintained by public individuals, that there could be the introduction of a malicious actor, right? So you've seen it in the news. I mentioned event streams in my talk as far as a technology kind of pattern goes, but there was an actual package called event stream, right, in the Node.js ecosystem, and it had a dependency, right? So everyone depended on event stream, and event stream depended on something else, and that something else tried to monetize, and then it didn't work out. So then that maintainer wanted out. So then somebody said, hey, I'll maintain it for you, right? Mm-hmm. So it switched maintainers, and then on the next version of that dependency, they introduced, right, some malicious code dealing with Bitcoin and whatnot, and that got then ported in everybody's packages, and then it spread out everywhere. So that's an issue you got to worry about. So the likes of NPM and registries and Yarn and all these other kind of package managers, especially around JavaScript, which is where all this happened, are taking great pains to introduce, vulnerability scanning and these other checks as far as protecting the end, clients of those dependent packages. And then also, but ultimately the responsibility rests on yourself, right? If you're going to use these dependencies, and something bad happens to your clients, that is your fault. So the general strategy we go down to kind of mitigate that is heavy reliance on lock files, which is lock in your versions of your dependencies, right? Because this malicious actor that got in, right, to inject that code, they had to release a new version, right? And everyone just had to auto upgrade themselves, right? So when you have a lock files, or when you have a dependency like in JavaScript package.json files that just say, oh, well, I'll take anything that's version 5, right? Well, then a malicious actor can say 5.1, right? And then you're going to get it. So instead, lock your versions to the specific numbers, right? And then when you are going to upgrade, make sure you do it very deliberately and go ahead and vet as much as you can before you do so.
Very interesting perspective. So lock your version numbers is the umbrella statement. Thank you very much. We have a question from a viewer who wants to send and receive robot data via internet and is looking for a good method to do so. So I think your MVP and your whole infrastructure really spoke to this person. Do you use ROS Bridge Suite for the remote monitoring and control, or something else?
Right. So ROS Bridge Suite is supposed to be an out-of-the-box web bridge functionality in general, right? That I mentioned on our slides where we have a web bridge. For certain reasons that are older than my tenure, they thought that it wasn't customizable enough, right? So we wound up rolling our own kind of bespoke web bridge to be a little bit more flexible to fit our solution, right? So there's no ROS web bridge suite in our overall system right now.
And did you use any kind of a robot simulator for your whole?
Right. So there are plenty of robot simulators. So there's two sides of our house, right? So there's the robotics team and then the cloud team, right? So the robotics team has plenty of robot simulators to speed their development, right, and simulate certain things. And the cloud side is nice because, again, we go from the browser to the cloud to then the web bridge, which ends at ROS, right? So for our robot simulator, we don't have to do anything super fancy as far as sophisticated robot simulators. All we have to do is mimic the ROS requests and responses right there. So we do have what you would call for the cloud team a robot simulator, but it's nothing more than a Node.js script that mimics actual requests and responses. We can measure it on the edge.
And that helps kind of compartmentalize the team so you can make parallel progress instead of waiting on the other, right? I'm sure your robotics colleagues, still use the run-of-the-mill simulators that any of such robotics development would require, like Gazebo, Arviz, MoveIt has all these integrations. Right. So, I'm fairly certain, given the scope of the problem of random bin picking, I'm pretty sure simulation was used, especially if you're training your models, because that's exactly how you would test it. You won't test it on a real arm, right? Otherwise, it could just break physics.
Sure, exactly, yeah. So if you go back into the customer experience center where all the robots are and everyone can see them, you'll see Arviz up, all those kind of cool. They have all the cool toys, right?
Right.
But definitely, thanks to ROS, right, with that defined interface. So we have two of them. We have the ROS defined interface and then our GraphQL layer, right? Mm-hmm. Anybody familiar with web dev? The GraphQL very strictly defines that interface. So it's nice that as long as you appease those kind of contracts, things can click in and out, like we talked about. Right. So it makes parallel development a lot more frictionless than it would be.
Yeah. So now that I make a mental model of the division in your team, I see a lot of our questions are actually focused more towards your colleagues on the robotics side.
Of course.
Right. But we still have some some of them on the cloud side. So something up your alley, since you have talked about a serverless architecture, and there are these schools of thoughts on server architecture versus serverless architecture versus Kubernetes. So at what point does it make sense to switch from serverless to Kubernetes, as you did as well?
Right. So the main drivers behind our switch were the code portability, right? Because we had the clients that want to either specify their cloud vendor or they want to say, no, we want it all on-prem. So put it on our bare metal and let's all have it in-house. So that's one key, right? So if you're trying to decide between serverless and something like Kubernetes, know your clients, right, before you start your project and go too far down one path. So if you have an inclination that your clients are going to have these kind of concerns about where their data live, that's something to consider off the bat, because like I said, the serverless code is per vendor, right? And there's certain business incentives for them to kind of not mind that vendor lock-in, right? That and the other one, which was your dev process, right? So again, I mentioned it in the talk where, at least at the time we were using it, it was very time consuming because you have to do some code and push it to your cloud to see it run, right? Mm-hmm. All the different pieces are designed up there to be kind of very independent. So you could test independent pieces, but you couldn't get it all. You couldn't get your whole stack running on your box. Mm-hmm. So having the Kubernetes able to do that, it sped things up. So perhaps even now or soon, I'm sure these cloud vendors with these serverless offerings are it behooves them to make that development process more smoother. So by that time, if you were thinking about a project for serverless architecture, make sure that you can run it all on your box, and that'll speed you up much faster. So those two main concerns
where our driver behind us migrating over to Kubernetes. But if I were, say, doing a garage startup, and I have, you had an idea for some app, right? And right, you could get it to run on your box, and you wanted to go quickly. It's very good for speed to market, right? And again, you don't have to worry about any of the infrastructure stuff. So you get a lucky press release, or you do an Ubuntu Masters talk, and then everyone loves it, and suddenly you have a million requests per second. Something like Kubernetes, we have our auto scale, but we would still have to worry about it. With the serverless stuff, you have the entire weight of that vendor behind you.
That's one of the biggest advantages, the biggest selling point that serverless architecture brings to the table, right? Which is, there's this huge mess of wires and servers, and you don't have to worry anything about it. And in the off chance that you really do get famous and viral, we got your back, right? You don't have to worry about it. And also, there's the other part, right? The story doesn't end there. When the viral spike actually goes down, we still got your back, right? You're not, it downscales as well, which is you're not paying for that inflated level. You're only paying for whatever you're serving or whatever you're making.
Right. So it just takes some upfront analysis, right? But it's not that hard of an analysis to perform to determine which way is the best way for you to go.
Yeah, absolutely. So I think we have time for one last question. Right. So we'll take a step back, right, and talk about the language. So you built your MVP in Python, and then you had this massive rewrite in JavaScript. What attracted you to choose JavaScript? And why did you move away from Python?
Right. So JavaScript in general, I think the advent of Node.js, because, as we all know, JavaScript started in the browser, and with Node.js, it became, able to run on the server with all the good things that come with it. There's hardware acceleration now, access to the file system, etc. Having that all the way down the stack, for me was, there's technological reasons, right? You can talk about its event loop and its single thread, but and the asynchronicity that's good with it, and of course the rich libraries. But for us, being a small startup without a large, human resource pool, right? It's easier for us to have full stack JavaScript that's still performant, but we're in San Antonio, Texas, right? So bringing in labor to work on the code, if you have somebody who is, say, a React developer but is still decent on things like, Redux and state management and other things like that aren't so self-assured on the back end, you can eventually train them, not without too much investment, to then migrate to work on the server and then even down on the robot. So then you have a front end web dev that's eventually doing robot programming in JavaScript. They like it, and for us in our stage of our life cycle as a company, it works.
Right. So, and I think a lot of companies can identify with that. So it comes down to the economics of manpower, right? And the tradability between the transferability of this manpower across stacks, right? Very well. Yeah, thank you so much for that. And with that, I think we're at the end of our talk. So thanks once again, Zachary, for this interesting talk and also for this lively discussion. I really enjoyed it, and I'm sure our audience felt the same way.
And one more note to the audience. You saw the email. I would be happy to forward your robotics-specific questions to the roboticist at +1, and we'll get back to you.
Yeah, so feel free to contact Zachary, add him on LinkedIn, spam his inbox, and I'm sure he'll be happy to cater to his to your request. Just a quick reminder for our audience that the recording of this session will be sent to you automatically. You can also visit ubuntu.com/masters-conference to view past sessions. And this talk will be followed by our last session, our third and last session for the day, hosted by my colleague Sohini Roy on multi-cloud. And I hope that you stick around to check that one out as well. Thank you once again for all your questions and for being a wonderful audience. And thanks once again, Zach, for the presentation.
You're welcome. Have a great day.
Bye.